Section 12.3 is on infinite sequences and series. So we're still talking about sequences of numbers, and sometimes in theory they can go on forever. And when that happens, you have an infinite series. So an infinite series is a series with an infinite number of terms, or it's just never ending. So for an example, the following is an infinite series. 1, 1/2, 1/3, 1/4, 1/5. It would go on 1/6, 1/7, 1/8, and on and on and on. The nth term would look like 1 over n, right? So if it was the 36th term, it would be 1 over 36. And as n gets bigger, so it gets, 20, 30, 40, 50, 1,000, 5,000, 10,000, the function gets closer and closer to 0, but never actually reaches 0. So if you think about, 1/5 is smaller than a fourth, 1/10 is smaller than a fifth, 1/100th is smaller than a tenth, 1/1000th is even smaller, and so on and so on. These numbers are getting very close to 0, but they're never actually going to be 0. So 0 is called the limit of an infinite sequence. So whatever number the sequence is approaching, that is called the limit. If you go on to calculus, you'll talk a lot about limits and how series approach different numbers. But for now, we're just going to look at how to find the sum of infinite series. So looking at this infinite series, 1/5, 1/25, and 1 over 125, we can see that this is a geometric series. To get from one term to the next, we're multiplying by a fifth. So this is a geometric series with r, or the common ratio, equal to 1/5. If we wanted to find the sum of the first 100 terms, we would use our sum formula for geometric series, which would say the sum of the first 100 terms equals the first term minus the first term times r, which we decided was 1/5, to the n, which would be 100, all over 1 minus r. When I simplify this out, when I'm looking at the bottom here, I'm going to just keep the top the same. 1 minus 1/5 times 1 over 5 to the 100. 1/5, this is the 1 is the same as 5 over 5, so this simplifies into 4 over 5. I'm going to simplify this by saying I'm going to take my fraction here, I'm going to flip it so that I can multiply the entire thing by 5/4 and get 1/5 minus 1/5 times 1/5 to the 100th. My 5's are all going to cancel here on the ones on the outside. These will cancel there. The one inside the parentheses with the 100 stays the same. And I'm going to end up with 1/4 minus 1/4 times 1/5 to the 100th. When I think about the number 1/5 to the 100th, that means I'm taking 1 to the 100th over 5 to the 100th. 1 to the 100th is 1. 5 to the 100th is a really big number. And as that number is really, really big, that means that fraction is really, really tiny. So this number is approximately 0. So what that means, if I were to plug in 0 here, it's approximately 0. 0 would multiply with the 1/4, and this would all cancel, and my answer would just be 1/4. So no matter how many terms are added to the sequence, if I decide to do the sum of the 3,000th term, I'm always going to have 1 over a really, really big number, which means I have a really, really tiny fraction that is very, very close to 0. So no matter what, my sum is always going to be no greater than 1/4. So the sum of this infinite series is 1 over 4. So we can have a formula, a general formula, for the first sum of the first n terms of a geometric series where the common ratio is between -1 and 1, or that can be read as the absolute value of the ratio is less than 1. All this means is r is a fraction. It's less than 1. It can be positive or negative, but it has to be within the boundaries of 1 and -1. So we have this formula. The sum of an infinite series can be given by the first term over 1 minus r. If we look at the example we were just given, the first term was 1/5, and we decided r was also 1/5, so we had 1 minus 1/5. If I simplify this out, this is 1/5 over 4/5. Okay, using my fractions, this 5 comes down here, this 5 comes down here, or up there. I get on the numerator, I get 5. On the denominator, I get 20. And when I reduce that, I get 1/4. So you see I end up with the same sum there with this sum formula. Oh, I was going to write that here. That's why I left that space. So if you want to do that there, that's fine. So let's look at an example. Find the sum of the series 60, 24, 9.6. So we have an infinite series. It's going on forever. And I'm adding up the terms, and I'm going to use my sum formula. My sum formula, again, is a sub 1 over 1 minus r. So my first term, obviously, is 60. R I'm going to find by taking my second term, 24, over my first term, 60, and that is going to reduce to 6 over 15. Remember, I need r to be a fraction between -1 and 1, which it is, so I can use this formula. So all I'm going to say is the sum equals the first term, 60, over 1 minus r. Again, 1 is just 15 over 15 for a common denominator. So this is going to be 60 over 9/15. This 15 comes up to the top here. When I multiply that out, I'm going to get 900 over 9, which will be 100. So the sum of this series is going to approach 100. So I'd like you to find the sum of this next series. Please try that out. You should get 147 over 8, or as a mixed number, that's 18 and 3/8. So try that out. Okay, the last example we want to do is we can use infinite series to rewrite repeating decimals as fractions. So whenever we see this line above a decimal, we know that that's repeating. So this number is 12.981981981981. It just repeats in that pattern. So we're going to use this to rewrite it as a fraction. Obviously, 12 is a whole number, so we're going to keep that out front and just deal with the fraction for now. So we can write 981 goes to the thousandths place. So what we're going to do is we're going to take 981 over 1,000 is equivalent to 0.981. So that's going to be the first term in our series. Then it's going to repeat again in another 1,000 decimals. So I'm going to add just another 3 zeros underneath. So I'm going to have now 981 over essentially 1,000,000 here. And I'm going to keep doing this because this decimal keeps repeating and it keeps moving down 3 decimals places. So every time I'm just adding 3 more zeros to my denominator. And so on and so on and so on. So I'm going to look at this as a series now, where 981 over 1,000 is my first term. My r, or what I'm multiplying by every time, is 1 over 1,000. I'm just multiplying my denominator by 1,000 every time, so my common ratio is 1 over 1,000. I'm going to use my sum formula and say the sum is the first term, 981 over 1,000, over 1 minus r, 1 minus 1,000. I am going to simplify this out. So remember, 1 is just 1,000 over 1,000, so I can get a common denominator there. This is going to be 981 over 1,000 over 999 over 1,000. When you do your fractions, if your denominators are the same, they will cancel. So you're going to end up with 981 over 999, which reduces to 109 over 11. So that's the decimal, or that's the fraction representation of the repeating decimal, and the final number would be 12 and 109 111ths. So try and do the next one. You're going to do the exact same process. Again, you're dealing with 3 decimal places, so you're going to be dealing with fractions in the thousands. Your answer should be 254 over 333. So see if you can get that answer. Write down any questions you have. Please don't forget you have a quiz tomorrow on 12.1 and 12.2. So just make sure you can do all of the practice problems we've done so far. See you guys tomorrow.